Aloha. In this video, we're going to do lab 8.6, a MIPS assembly language program to compute the Fibonacci sequence. So I've got the lab here on the screen, and the idea here is we're going to start the array. It's going to create an array with Fibonacci numbers in them. The array is going to start at location 5000, and then it'll increment up. It's 4 bytes per integer on the MIPS machine. So the first integer will be at 5,000, the second one will be at 5,004, 5,008, and so on. So if you look at the MIPS simulator assembler in section 3.10, I'm going to open that up in a new window. We see this is a good place to debug your code. There's a simulator here. There's also, if you're going to do some I/O here, there's also a simulator with assembler, and we're going to use this to produce machine code to test our assignments at the end. But right now, it's fine that we use this. This is nice because it shows the registers that are valid for our little MIPS ZY machine. The MIPS machine actually has more registers and so on, but we're keeping it simple. And so we're going to use this, and by convention, we start our data memory at location 5000. Doesn't have to be that, but that's what we're doing. And we use these 7 registers, 0 through 6. And there's a register called 0, which just contains 0. It's read only. And then we also have a register which we identify as SP, which stands for stack pointer, and RA, which stands for return address. And we will use those registers in the later assignments in our later in labs 9 and 10, and in this the second or the third and the fourth assignment, or the fourth assignment. All right, but we'll get to that later. All right, and also for this problem, let's see, I'm going to put this right here. Also for this problem, we're going to stick with, if we look at instruction memory, these are all the instructions, the valid instructions in the in our little MIPS ZY machine. It's a subset of the full MIPS instruction set. And so far, our first assignment, our first programming assignment, we converted the C simulator into Python, you recall, or if you've gotten to that yet. And that simulator simulates the ADI instruction, the ADD instruction, the LW instruction without offset, and the SW instruction without offset. You can take a look at that. Trust me on that, I guess. And so we're going to stick with those, with just using those instructions, except for our Fibonacci sequence. Our Fibonacci program has a loop, so we're going to use the jump instruction to jump back to jump to a different location in our program, and we're going to use the BEQ instruction to branch if a register is equal to 0. Branch if the values held in A and B are equal. Oh, that's where it is. Okay, so if A and B are equal, then it jumps to this label. And of course, in assembly language, we need to label certain instructions because those can be addresses that we jump to. All right, so let's go back to our assignment here, and I'm going to close this, and I'm going to make this smaller so we can see both the simulator here and the assignment. Okay, so my approach is going to be, first of all, we see that the number of iterations, or the number of of elements in our array that we're going to produce is stored in T0, and in this example here, let's just try to replicate this example here. That would start out with the value 5, and the address that we're going to store our array at, the first location is going to be at 5,000. So I'm just going to put 5,000 here, and that's T0 and T1. So that's the initialization, and then we enter in our program, and when the program is done, it should have 0, 1, 1, 2, 3 in here, 0, 1, 1, 2, 3, because we're only going to go up to 5. And before this is over, we'll test with 10 and 15 and some larger numbers to make sure that they work. Okay, so to start things off, I'm just going to write store. I'm going to store the value 0 in 5,000. Then I'm going to store the value 1 in 5,004. And then I'm going to iterate. For the next location that needs to be stored, I'm going to take the previous location, put that in a register, take the previous location from that, put that in a register, add the two together, and store it in this new location. And then I'm going to decrement the counter, increment the address pointer, and then do the same thing again to compute the value that goes into this location, which again will be grab this one and grab this one, add the two together, and store it here. All right, so let's start out by doing what I just said. We're gonna and we're gonna use this ADDI instruction where we're gonna make, basically what this does is it takes a value, some value that's in the instruction. In this example, it's 7, and we add it to the value that's in this register, and we store the result in this register. So we're going to use the 0 register for 0, and we're going to use this register to be the constant that we're going to store in there, and the first constant that we store in there is going to be 0. And then that's how we're going to store the result in this register. And then after that, we're going to use the store word instruction to store that register into the memory location whose address is in this register, which in our case is going to be T1. All right, so those instructions would be ADDI, and I'm going to the other thing is I'm going to use T2 to buffer, to store the value that I'm going to this is going to be the result of the computed next computed Fibonacci number, and that's the number that's going to be stored directly into the memory. So I'm going to store into T2. That's this buffer here. Store into T2 0 register 0 plus, and the constant is going to be 0. So this means load T2 with 0. Okay, and then I'm going to store that out. This location's already initialized, so I'm going to store word. Store word. The value that's in T2, store that value into the memory location whose address is in T1. Let me make this a little bigger. Okay. And this basically stores T2, which in this case is 0, into the memory location memory address, which is in T1. Some sort of convention to display that. Okay, so now after this is done, I'm going to make this a little bit bigger. So after this is done, we should see a 0 here. Well, there's already a 0 here, so that's kind of uneventful. Let's do the next one. ADDI into T0, I'm sorry, T2, that's our buffer. 0, the value 0, plus 1. So that's going to put a 1 into T2. So this is going to load R2 with 1. And then we're going to store that T2 into O. This isn't going to work because I need to increment T1 before I do this. So let me do that. Oh, I need to do two things. I need to increment this value by 4, and I need to decrement this value by 1. So let me throw that in there first. I'll just go like this. We need to increment T0. So I'm going to do add, storing the result into T0, T0 plus 1. Add 1 to T0 and store that into T0. So this, I'm sorry, I got a minus 1. I'm decrementing. I could use a subtract instruction, I think, but I'm going to just use the add instruction and make it so it stores minus 1. Maybe I make this bigger. Oh, that's fine. Okay, so this is going to subtract 1 from T0. Okay, and then so that's gonna make this go down to 4, and then I've got to add 4, the value 4 to this one because that's the next address. It's 5004, you see. So I'm going to add into T1. That's our address register. I'm going to add 4 to T1. Add 4 to T1 and store the value back into T1. This is incrementing address register. I'm just going to call it that, okay? So that will set it up for the next storage. So now T1 is going to point to 5004. It's going to be that. T0 is going to be 4, and then it's going to be able to add. Then we're going to go ahead and put a 1 here. So, and this is pointing to this. This is pointing to this. So we're going to load a 1 into T0. So this is going to be a 1. And then we're going to store that value into the memory location whose address is in T1. Okay, so it's just like this. Okay, and so that's going to store this into here. I'm just going to make that a 1, and then I need to do this decrementing the counter again and incrementing the address register. So I'm going to just copy this here, paste it down here. Okay, so after this is all done, if we start out with this being 5 and we start out with this being 5,000, we should have, let's make this 0, make this 0, and we should, when this is done, then we should have a 0 here and a 1 here. This should be 3 because we've done 2 of them already. This should be 5008 because we've done 2 already and we've incremented to the next address register. And this should be 1 because that was the last value that was stored into here. So let's just run this simulation and see what this looks like. Enter simulation. And instruction is there. I think it should be add I. Okay, so let's fix that. Can I do that? Now let me, oh, there, add I. And this is add I also. Oops. Okay, so first mistake. Okay, good. Let's enter the simulation again with no errors. And let's step through it. 5,000. 0 gets stored there, gets stored there. That gets decremented by 4 to 4. This it's incremented to 5004. We store a 1 there on T2. We store that 1 out here into 5004. And here we are. We're going to now decrement this to 3. And we're going to add 4 to T1. And now it's 5000. Okay, so it looks like we've done it for Fibonacci for the first two Fibonacci numbers. All right. Now, so the number of Fibonacci numbers left to be computed is in T0, and the next address is always going to be in T1. There's one thing that we there's one thing that we missed here, and that is that assume the array size is always at least 1. Well, that means that the array can be 1, just 1. And if the array is just 1, then we want to stop after this. Okay? We want to test it. Yes. Yes, we want to test it here. Okay, so let me exit the simulation. And right here, we're going to test to make sure we're done. I mean, we've decremented this down. Basically, what I don't want to show it, but well, in fact, I can't show it. I'm going to put this at 1. I'm going to make this 5,000, and I'm going to run this, and you can see what happens. I'm going to enter the simulation, and this is just set to 1. I only want 1 Fibonacci number. We're going to see that this isn't going to work because we go through, and then we should have stopped there, but we didn't. We keep on going, and then this gets decremented down to -1, and then we keep on just running forever. Okay, it doesn't stop. All right, so let's fix that. Exit the simulation. Let's fix that. Let's put a branch if equal if T0, which is our counter, array counter, if that is equal to 0, then branch. I'm going to say L2 or end. I'm going to branch to end. Okay. And so we have to, this is a label. So we got to put the label, we have to say where the label is. I'm just going to say it's right here. Okay, so when we're done, we branch to end. Okay, now it should work. Let me just run this and see. Branch if T0 is equal to 0 to end. Okay, so enter simulation, and I'm going to do fast. Okay, so now we just run. 0 gets stored there. That gets incremented. The test happens, and it jumps to end, and now we're done. Okay, so that seems to. It looks like it works. Okay, so now let's continue on here. Exit the simulation. So now what we need to do is we have to test again because we've just decremented. Every time we decrement T0, we got to test to see if we're at 0 yet. So we've decremented T0. It doesn't. These two, it doesn't matter the order. Maybe it makes more sense to. It doesn't matter the order, but maybe it makes more sense to decrement the T0 counter and then test it. So I'm going to do the same thing here. I'm going to close these up a little bit. I'm going to put this thing right here. Paste. Okay, so this loads the first one, decrements the counter, increments the address register, and then tests to see if the counter is 0. If it's not 0, then it continues on. It loads 1 as the next Fibonacci number, stores that 1 out into the proper address location, increments the address register by 4, decrements the counter by 1, and then tests to see if the counter has hit 0 yet. If it's hit 0, it jumps to the end. Otherwise, we are ready now to do our loop. And our loop is going to be we are now on 5008. Okay, we want to compute this number. So the way I'm going to do it is I'm going to use these these LW with offset. Now, what that is it's the same as the LW, except for this 0 is no longer 0. It is an offset. It is an offset from the address that's in here. So right now, in our case where we are, the address is 5008. Well, I want to load up whatever is in 5004, which is 1 back, and then whatever is in 5000, which is 2 back, and then I want to add those two together, and that's what I want to store into the 5008. So I'm going to use the LW, and this offset is going to be -4 the first time because I'm going back 1, and then the second time I'm going to load -8. And this will be the register. This will be T1, which is where I'm going to store the new number. So let's go back to that. So I'm going to first of all I'm going to load word. I'm going to load into and I'm going to use T3 to store the previous number. To store what will be the previous number. I'm going to store that in T3, and I'm going to use T4 to store the second to the last previous number. Okay, so I'm going to load up T3 with this number, then I'm going to load up T4 with this number, and then I'm going to add the two together and store that result into T2. And then it's stored in T2, and it's ready to be stored out at the next address location. So let's load word. Load into T3, load into T3, -4, whatever the address is in T1. So that this is going to load last fib number. And then I'm also going to load word into T4, load into T4, the second to the last Fibonacci number. This is going to load second last fib number. Okay? So now I've got the two numbers in here in T3 and T4, and then I'm going to add the two and store the results into T2. So that would be add, just a plain add, store into T2, whatever is in T3 plus whatever in T4. This is compute next fib. And then now the result is in T2, and we're right back where we are here. Where the result is we're going to store the result of T2 out into T1. So I'm going to copy this, same instruction, so why not? Copy this here. And then, so I've stored the next value, and then I've got to do this decrement, increment the address register, decrement the counter. So I'm going to copy these two things. Okay. So this is store the Fibonacci number, and then this is increment the address register, decrement the counter. T0 is the counter, and then I got to test to see if it's 0. Now I don't need to replicate this. I can just jump back up to here, and then that's to the continue of the loop. See, so this is like a while loop where we test at the very beginning to see if a condition has been met to end the loop. If the condition is not met to end the loop, then we do the iteration part. Okay, so I'm just going to put a label up here, and I'm going to call this label L1, label 1. Okay, And so that's, and then I'm going to jump back from here. I'm going to jump back to label 1. Okay. So I'm going to say, this is like jump to top of while loop. I'm just going to say that. Okay. So once we've tested and we find out that we're not done, t0 does not equal to 0, does not equal to 0. So then we're going to load this last Fibonacci number. We're going to load the second to last Fibonacci number into T4. We're going to add T3 and T4 and store it in T2. We're going to store T2 out to where T1 is, to the address that's in T1. Okay, and we're done with that. And then we're going to increment the address register by 4, decrement the counter by 1, and then jump back up here to test to see if we're done. Jump back to O1 to test to see if we're done. Now we can actually do this if we want to make this look better. We can do it that way. Okay, in fact, if we indent this a little bit, it looks almost like, sort of kind of like how a while loop should look, you know. Oops. Okay, so this is our while loop here. All right, so let's test this. Let's start this out with let's start this out with 5, just like this, okay? And start with this out with 5,000. We can start this with 0. It doesn't matter. These are all 0. And let's enter the simulation, okay? And let's make this be fast. And let's just click run and see what happens. See if we can follow it. It computes 0, stores it there, decrements, writes 1, stores a 1 there, increments, decrements, gets the 0, gets the 1, stores the 1 out here, decrements, increments, gets the 1 and gets these 2, computes the 2, stores that there, gets the 2 and the 1, stores that here, 516, goes to 520, gets the 1 and the 2 and computes it to 3 and stores the 3, and then that decrements T0 to 0, and then we're done. All right, so it looks like it works. This is 1, 0, 1, 1, 2, 3. 0, 1, 1, 2, 3. Let's test it with a much larger number. Let's make this back to 0. Exit the simulation. Let's put this back to, oh, okay, great. Let's make this 10. Okay, and we can, more options. Let's set this to instant, and type enter simulation and type run, and there it is. So now we can see these are the first 10 Fibonacci numbers. It goes all the way up to 36. This is where we would store the next one, but we've decremented our counter already. But we can see this remnants here, 13 plus 21 equals 34, and that was the last one stored here at 536. All right, so that looks like that'll work. Let's take this. Take this all the way to the end here. Let's copy it. Let's go over here and paste it in here, see what happens. We need to initialize T0 as 5, let's say. And we need to initialize T1 at 5,000, of course. And let's just start this out at 5,000. And it will add memory locations visible as they get written. So let's just do the same thing. And let's enter the simulation and let's run it. And lo and behold, 0, 1, 1, 2, 3, 520, that looks good. And let's try 10. I'm going to try 10. I'm gonna try. How about if I go for broke and try 15? Enter simulation and run. Whoa, those are the first 15 Fibonacci numbers. And we can submit for grading. And looks like we got all of our points. Hope this helps. Thanks for watching.